Hello, I'm Mumnik. I will be doing today's KDForce second division round, and I will try to explain what I'm doing. In problem A, we're given two arrays of equal lengths. We can do unlimited number of operations. In each operation, we can swap two elements on the same position in two arrays. And we want to determine if it is possible to make the last element to be the maximum one in both arrays. Okay, so if we take maximum of these two equations, we should get that maximum of an and bn is equal to maximum of all the numbers we have. We cannot change the set of numbers, like multi-set of numbers we have. So, and the two last numbers, they will remain two last numbers. We cannot change the positions. So, the bigger of two last numbers must be at least as big as all the elements. If it is not true, then the answer is just no right away. Otherwise, let's say that bn is the bigger one. If not, we can swap them. And then, so in array B, this will be true for sure. So we need to check if on each position the smaller of the numbers is at most an. And that's how we check the answer. Right. That was an important one. So yesterday I updated macOS and I think that all the snippets I had are lost. Not all of them, but like all the snippets that were in the correct folder are lost. So I have some that I ported from my old laptop, but they're kind of outdated. Yeah, I will need to restore the snippets that I want to have. For now, I only restored mint and segmentary just because I used it in the yesterday contest. So, for example, I don't have snippet to do multitest right now. Okay, so if the last element in A is greater than the last element in B, I should swap them. And now, well, basically I need to go through all the elements, all the positions, take two elements, make smaller to be in A. Well, I want to check that all of them are at most the last element of B, and the smaller is at most the last element of A. but I can sort those two elements and just check that, well, now x is the smallest and y is the largest. So I just need to check this. In problem B, there is some kind of lottery. I guess there are people that are numbered in some way. The lottery will be held on m consecutive days. Well, it doesn't matter that they're consecutive, just m different days that are ordered. Each day there must be exactly one winner. And that person is not allowed to participate later. We don't know the winners. We need to, I guess, find possible winners for each day, or say that it's impossible. So for each person, there will be the last day when they participate in lottery. On all the previous days, they cannot win. So we can, for example, for each person, store the last day they participated. And for each day, we will store a set of participants that could have won. While reading the input, like when we read the next day, we read all the participants on that day. For each of those participants, if they participated earlier, we have to say that on all those days they did not win. Since we store for each participant the last day, only on that day we thought that they can win. So we have to remove them from the set for that day. And if we do that, after we process everything, for each day we will have a set with all possible winners, and then we can just take any element in each of those sets, unless one of them is empty, in which case it's impossible. Yeah, I think that works. And the complexity of that is, well, size of input times log, because for each basically for each input element we do constant number of operations with maps and sets and stuff. So we have n days. Well, it was m. There is a map that we will use to store for each participant its last day, and those other sets we should clear them from the previous runs. So on each day we have k participants. We read them one by one. If that participant is already present in map, then we should remove them from the set for their last participation. And now we are saying that last participation for this participant is on day I, and insert insert them in the set for this day. So many letters. Well, let's start to say it out loud, because otherwise I will forget it. So there are n types of candies. For each candy we know the cost of one candy of the type, and we know how many candies of the type we have. We need to pack candies in packs, and each pack can contain only one type of candies. Moreover, for each pack with one fixed type of candy, the number of candies in all those packs should be the same. So we have to choose integer di, which will be the number of candies of type I in one pack, and ai, the number of candies of the type, should be divisible by di. Then one pack of candy of type I will contain di candies, and therefore the cost of that pack will be bi times di. Okay, so I guess we should do that to save on price tags. Sure. So we will put the packs of candies on the shelf in the order they are given, so they should be um, 1, 2, and so on, n. We cannot change the order, I think. And if consecutive packs have the same cost, then we can put one price tag for some segment of candies. Yeah, and we want to minimize the number of price tags. Amazing statement. And the limitations A up to billion, but B are kind of small. Few seconds. Like, we surely can do DP like the last price tag, like we go left to right, and for the last price tag on the this candy, well, for fixed price, what is the smallest number of price tags we have already used, and then to make transition, we will have to use another price tag if the prices are not the same. So we kind of need to like know the minimum over all previous DP values and whether there is a DP value with this particular number. And so we can do kind of 2 pointers. The number of states will be sum of number of divisors of AI, which is reasonable. Like maximum number of divisors, I think, is less than 2000 for numbers up to a billion. It's a bit of an issue to find them. And we then probably should like sort them or something to do 2 pointers. It's kind of on the border of what can pass, but it seems like a stupid solution. Maybe there is something better. Okay, so if we like a valid price for is candy should be divisible by cost of one candy, but should be a divisor of cost of all candies, right? So like bi times di is the price of a pack, and di is positive integer. And if we then multiply c by ai divided by di, which is also a positive integer, we will get ai times bi. So for given position I, the price is valid if it is a divisor of ai, but divisible by a divisor of ai times bi, but divisible by bi. So if we want to set the same price for a segment of candies, like that price should be divisible by all bi's and should be a divisor of all numbers ai times bi on that segment. So that means that LCM of bi's should divide that price, and also the price should be a divisor of GCD of numbers ai times bi. So we can actually do greedy, just start somewhere. Well, yeah, the fact that we should be able to do greedy was obvious from the start, like should have been, but I didn't thought about that. Like start, then run to the right, and while we can use the same price for that segment. If we can't, then we should have stopped before that, and okay, we must use a price tag for those candies, and we can do with one. So just cut there and run further. And the thing I said previously about GCD and LCM explains how to implement that. So we will maintain LCM of BIs and GCD of AI times BI while running. And the situation is good if LCM of BI divides GCD of AI times BI. That's a cool problem. Why the limitations are like this? Okay, small BI I don't think that helps, but they could have made bigger AI, like so that A times B still fits in Hong Kong, and bigger N. I don't know, it feels a bit weird, but okay. So we don't even have to save all the values. Thankfully they are given like AB and not first array of A's and then array of B's. So we read yeah. So A will be GCD of A times B, and B is LCM of all B's. So here we should say, okay, A is GCD of A and X, B is LCM of B and Y. Yeah, before that I should have multiplied X by Y. I think that I understand why B up to 10 to the 4th, because well, we know that GCD can only be smaller, so GCD is always bounded by 10 to the 13th, and we will continue only if B is a divisor of A, so it is again small. So it is at most 10 to the 13, but like in this LCM function, we take LCM of numbers that is potentially up to 10 to the 13th and 10 to the 4th. So the LCM will be just 10 to the 17th, and it fits in long, but like we could have just like here we should check that this LCM will divide A and A after we taken GCD. So if A mod B is not 0, or A divided by B mod Y is not no, that's not correct. Well, we can say that let's take GCD of B and Y, and then divide Y by G. Now LCM will be just product of B and Y, which can be big, but now we can write what I wrote previously. So if this already doesn't divide A, or if it divides but the result of division is not divisible by Y, then we should stop. Yeah, let's divide B by G. Then X and Y are untouched, and we just say, okay, before that we should have stopped the previous segment, and current values will become just X and Y. Yeah, and now that would work just if it's guaranteed that product of AI and BI is up to 10 to the 18th, no, fits on long. Yeah, and that probably would be slightly better problem, but this problem is cool. Did not copy it? Probably should have used the other compiler, because that's a lot of module operations on longs. Yeah, cool problem, bad choice of limitations. Like, I'm sure it's possible to get accepted with factorizations. It's much worse. Okay, so in problem D, we're given a multi-set of numbers. Look, we said that it is array, but we can rearrange it how we want. And we know that the sum of those numbers is exactly 0. We need to rearrange the elements of the array such that if we find maximum by modular by absolute value sum on subsegment, it is strictly smaller than the difference between maximum and minimum element of A, and this thing is fixed because we cannot, like, we don't change multiset, so maximum and minimum will stay the same. And we have to say yes or no, and if yes, print the answer. Strictly small. So this thing is just like maximum spread between prefix sums, right? Like sum on segment is difference of prefix sums. So if we take maximum prefix sum and minimum prefix sum, their difference is this thing. So basically we want to rearrange our numbers such that spread of prefix sums is strictly smaller than spread of values. It's easy to get not strictly, right? We just like if our current prefix sum is positive, we put something negative next, and if current prefix sum is negative, then we put something positive. Then all the prefix sums will be not strictly between minimum and maximum. Oh, but actually, if I do it like I said, like when the current sum is 0, we do the same thing every time. Then we cannot go to minimum value if it is strictly negative. So impossible only if the array is all zeros. Otherwise, just take all the positive values, all the negative values. Let's put zeros, whatever, to positives. Yeah. So we are able to put all of them, and then just run left to right, and if current sum is strictly positive, we put something negative. That way our current sum is always strictly greater than the minimum element, because we started with something positive and then added something. So we result with something strictly greater than that element, and strictly greater than the minimum element, obviously. And if the sum is non-positive, then we just choose any positive value, and then we cannot get higher than maximum element. Okay. That's, I think that's easier than problem. No, I actually need to read. Probably not. So we need to check if there is a non-zero element and put non-negative element in one vector and negative elements into the other. Here, like, you kinda should use long because some elements can be up to n over 2 times limit on elements, but I know that my solution works, so I should not get sum to be bigger than maximum element or less or equal to the minimum element, so it should fit in int. That's a cool definition. So we have an array of length m, and it is called a test if the first element is m minus 1. So you can read it as like size of array and then the contents of array. Then we can call an array a multitest if you can read it as b1 that called the number of tests, and then we can split the remaining parts into that number of arrays that are tests. That's cute. Okay, so function f from given array is the minimum number of replacements of elements by non-negative integers we have to do to make this to be a multitest. We are given an array of strictly positive integers, and we want to calculate function f for every suffix of this array of length at least 2. Something went wrong with this underlining. That will be confusing for people. Yeah. Okay, I guess I finally need to draw something. I need to understand the definition. First, we need to try to solve for just one array. Oh, interesting observation, the function is not 2, right? I can always say first number is 1, and then this number is n minus 2. Then my array is a multi-test that contains one test, and that test is an array of length n minus 2. So f is at most 2. That's useful to know. So we only need to check if it is 0 or 1. How to check that every suffix, for every suffix to check if it is a multitest? That should be easy, right? We the suffix, here's the number, and after that, like, we know the number that is written here, and then we need to skip that many elements and like jump here. So for every border, we can just say if we don't change anything on suffix, can we make it a multitest? Like, not can we? I mean, if we don't change anything in the suffix, is it true that this is a concatenation of some tests? And if so, how many of them there are? And to, like, we go right to left and calculate this thing. So for when we want to recalculate, we look at that number. If this jump is outside the array, then it's not a collection of tests. If it jumps somewhere, we look here. If this remaining part is not a collection of tests, then this thing was not a collection of tests. Otherwise, we take answer from here and add 1, because we added one more test. And now for every suffix we look at this number, and is it true that this sync is a collection of X tests? We just calculated that, so we just check. Okay, how to check if F can be 1? So there are two cases. Either we change this number, and that can be done if and only if the remaining sin is a concatenation of tests. So now we can assume that this sync is not a collection of tests, and we want to fix it in one operation. So we cannot change this number. So this number must be number of tests here. Okay. So I'm gonna start here. From here we jump somewhere. Here we jump somewhere. Then from here, like, it goes outside. So it's not a collection of tests anymore. What should we do? Like, we can change this number, we can change this number, we can change this number. If we don't change any of them, it's bad. Like, we already jumped out of the array. So what happens if we change any of those numbers? So if we change this one, we can make this arrow point anywhere to the right. So we would be able to make the number of tests, like anything we have seen on the right plus 1, exactly plus 1. So if we have seen x minus 1 on the right, it's good, because we know x. All right. If we don't change this value, then we jump here and then repeat the same thing. So that basically says that along with calculating the DP, like just what is the number of segments we concatenate to get the suffix, if any. We can also calculate what is the maximum number of tests we can make this suffix be if we want it to be a concatenation of tests in one operation. And how to recalculate that? Like, we're staying here. If it is not a good jump, we have to change it. Therefore, it's just like maximum number that we have seen in the first DP plus 1. And we can do that. Otherwise, we can jump here. That will increase the number of segments by 1. And then we can just ask for this suffix. What values are achievable? And it will say achievable everything from 1 to second DP of this point. So second DP in this point is maximum of this plus 1 for this segment, and like maximum value we have seen somewhere on the right that we just maintain +1. And they say that everything from 1 to that value is achievable. Why is that? Well, for this it is true because like if we have seen maximum, we have also seen -1, -2, -3, and so on. Like there will be a sequence of jumps that starts from maximum and then comes to 0 in the end. And we can take any of those numbers and add 1 to them. So we know that we can get 1. And here, like this thing actually meant that we can get anything from 1 to this number. Then we can choose any of them, add 1 to them, so we will get from 2 to this dp2 +1. And from this part we already got 1. So if this is bigger than this, then we like start at 1. Like we get 1 like this, and all others we can get by jumping like this. That's it. That's solution in linear time. So once again, we go from right to left. For each suffix, we calculate 2 values. Whether suffix from this point is a concatenation of tests, and if so, how many tests. We also maintain maximum of those values we have seen, and we also calculate the second DP. What is the maximum number of segments we can, maximum number of tests we can make this segment, the suffix to be, if we change exactly one number there, or like at most one number there. And it's calculated like this. And then for every suffix that we need to answer, we look here. We check if it can be done in 0 operations, just by checking that this thing is a concatenation of exactly X tests. Then if not, we check if we can do it in one operation, which can be done in 2 ways. Either we change this X, and so if this suffix is actually a concatenation of tests, no matter how many, we can just put that number there if we want. So that will be true. And otherwise, we look at this dp for this position and compare it with X. If X is at most this value, then all good. Otherwise, bad, and we need at least two operations, but with 2 operations we can always do like this. Cool. Cool problem from statement to solution. Great. I think I have seen something similar, but still, it's a really nice problem. I like this contest so far. So B is -1 if it is not a concatenation of tests, otherwise it is the number of tests it is a concatenation of. And so we have to look at so we're looking at value AI to determine where will be the end of this test if we don't change it. So it's I plus 1 plus AI. If B is strictly greater than N, BI is just -1. Else, if BP is -1, then BI is also -1. Otherwise, BI is BP plus 1. So now CI, the maximum number of tests we can make it be if we change at most one value. That's pretty much it. So now we are looking at suffix starting in I. If after skipping it, so we're looking at suffix starting in I plus 1, this suffix is a collection of tests and its size is exactly AI, then we're already good. So print 0. Otherwise, if it is a collection of tests but of wrong size, we can just change AI. So the answer is 1. If it is not a collection of tests, but we can make it to be a collection of tests of any size from 1 to Ci plus 1, including AI, then the answer is 1, otherwise the answer is 2. So problem F. We have k classes in each class there are Si students and the sum of Si is n+1. We wanted to order n+1 boxes of gifts such that then we wanted to distribute those gifts into classes. So i's class should receive exactly Si boxes, so the number of students there, and the total number of gifts in the boxes received by i's class should be a multiple of Si. But right now we only have n boxes. We're given number of gifts, and we are asked to understand what should be the number of gifts in the last box we still need to buy. And then actually distribute. Oh, that looks cool. N and k up to 200. So like sum of those numbers is very small. 200 is like very small, right? Like square root of 2n is just 20. So there can be at most 20 different numbers there. Don't know if it helps. And if we want to give some box to class I, we only care about the remainder modulo Si of the number of gifts in that box, right? Because we need to make sure that the sum of those numbers that we distributed to class I is divisible by Si. So we only care about remainder modulo Si. It feels like the LCM of those numbers cannot be that big. like their sum is at most 201. So if we want to get some LCM that is a product of prime powers, the sum of those prime powers should be at most 201. So what prime powers can we use? One of those, one of those. I probably should have done that on this computer. So what's the sum of these numbers? It's 50, 90, 120, so like 133. Okay, let's throw 31, 37 in the mix, just in case. So yeah, we don't need this one for sure. We probably don't need this one too. So again, the sum of all this is 133, I said. I think let's check. 30, 60, 110, 133, yeah. Well, just sum of all those. So plus 27 will be 160. So that's already greater. Probably better to, like, instead of doing this, because it only gives us like 3, it's better to save for this one. So with this one it will be like 164. So 171, so we have like 30 left, so this is also too much. So probably like this and up to 31. That's uh, 30, 101 exactly. Cool. And the product of those things, so our rough estimate on maximum LCM, which I think is a correct one, is the product of all those numbers. So it's like that's right. So this is 900 minus 1. This is 400 minus 1. this is also 400. Wait, this is divisible by 3. It's not prime. I'm stupid. Sorry about that. So, yeah, we don't have this one. Probably just getting 25 is reasonable. Or maybe like drop this, get 37. So it's like 37 divided by 4 and divided by 3. No, like getting 5 is better. So I do not have this sync, but here I have 25. Probably. So this is 400, and this is 100, this is 100, this is 400, and this is just 20. So it's like 4 times 4 times 18 times 4 times 9 times a lot of zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I expected it to be much smaller than that. So okay, it is so this is 64, 128 times 9, kind of 1,000, so it's kind of like 10 to the 14th power. That's a lot. Maybe like something insane is true. Like we can merge all the groups with the same SI. Like if we have 2 groups with the same SI, we need to have 2 subsets intersecting that each has SI elements that their sum is divisible by SI. Maybe we can instead find a set of two SI elements that their sum is divisible by SI, and for some reason it is always possible to split them in half such that each half is divisible. Oh, that would be true if no. uh, oh, right. If there is an element that the remainder modulo S that appears at least S times, then we can just take them out. So their sum will be divisible by S, therefore the sum of remaining elements will be also divisible by S. And if there is no such element, then we can split the elements in pairs such that in each pair two elements are different. Different. Is it enough for them to be different? Probably not. But like, it seems that should be correct. That's not a good good enough explanation, but yeah, I think I have to believe in that right now. So so basically what I'm saying is that if there are T groups, each of them of size S, then instead I can I want to have T subsets each of size S in which sum is divisible by S. Instead I can first find their union, a set of size T times S such that their sum is divisible by S, and then in such a set it is always possible to find S elements such that their sum is divisible by S, and I will find them, take them out, do the same thing until the whole big set is not of size S. So if I start with that, I will be able to finish in the end. Okay, so now is it possible that the answer is -1? It feels like even if I was just given some no. Can I do something similar? Okay, now, if I just believe that it is always possible, then I can do the following amazing algorithm. Just look at the groups one by one and try to find a set for them. If I will find a group for which I can find the set, let's just give them those numbers and just forget about them. In the end, I will be left with just one group for which I need to solve, and I will just add the box, add the number that creates correct remainder modulo zs, and that's it. Is it true that that's basically inductive proof that the solution always exists? The solution always exists for k equal to 1. If k is bigger, then okay, we need to prove that for some set we can find set of exactly that size that is divisible by the size. And what can we use? We can use that size is at most half of all the numbers we have, because like we can take the smallest and we have at least two groups. It sounds like it should be correct. But I kind of believe that. So basically, I need to prove that for any number n, if I have two n numbers, I can choose n of them such that their sum is divisible by n. I can prove it if n is prime. Yeah, if n is prime, then either there are n numbers that is the same modulo n and I can take them, or I can construct n pairs of numbers such that in each pair the numbers are different modulo n, and then I say like I take the first number initially, but I can switch to second in pair. That will surely change the remainder of the sum. And so what are the reminders we can get? Like we start with just taking the sum of first elements of each pair, and then we can add the difference between second and first. Let's do kind of knapsack with bit set. Like what remainders are achievable, and each time we can either choose to add D or not to add, and we shift our bit sets cyclically by something that is non-zero modulo n, and then take OR. Unless the bit set is of full ones, we will increase the number of ones in bit set. Therefore, we can get all the remainders in that. For non-prime n, that doesn't exactly work. But it seems like we can choose prime divisor of n and then create a lot of groups that are of size p and divisible by p, and we merge them together, and now we want take n divided by p groups in which sums are divisible by n divided by p. The only problem is that we cannot split all the elements in groups. We have to leave one group unturned, but I guess my proof actually worked for 2n minus 1 numbers. Yeah, and if we do that, like there's an inductive proof on divisors about 2n minus 1 numbers, then we should be able to show that among 2n minus 1 numbers, it is always possible to choose n numbers that their sum is divisible by n. I think there was like when I was a small child, I proved that for like when n is a power of 2, and there was like inductive proof start with 2, and among 3 numbers there will be 2 of the same parity, so you choose them, and to do inductive step you apply like for smaller power of 2 3 times. Now you get 3 groups of size half of what you want that are all divisible by 2 to the power of n minus 1, and then you choose 2 with the same parity after division by 2 to the power of n minus 1. So that's basically the same thing, but not for the powers of 2, but for all numbers. That's cool. Okay, do I actually have to write all the things that I said, or can I just do knapsack for 1s? For 1s, I take like 2s minus 1 numbers because I know that that will be enough. I take all of the modulo s, and now among those 2s minus 1 numbers, I want to choose a subset that is of size exactly s and divisible by s. So I need to do dp prefix number of chosen elements and remainder, and I cannot even use bit sets to optimize it because I need to restore the answer. I mean, yeah, I can use bit sets. But that's like cube as is. And I will just run it for values s that sum up to n. So that's n cube. Divide by 64 because why not? Yep. Okay, so my code will look as follows. I have vector of still available numbers. I will sort the groups by their size, and for all the groups except the largest one, I will go through them in that order. Well, the order is not important, just that I shouldn't do that for the largest one. And yeah, for the group of size s, I will give them 2s minus 1 numbers that I have, and will ask to choose s of them such that their sum is divisible by s. So that's a function. And then I will put the remaining numbers back into A, And then for the last group, for the largest group, I just calculate the sum, take modulo S for that group, and add the number that I need to make it divisible by S. Yep. I feel like the problem is not that hard. I just went in the wrong direction. Yeah, happens. Okay, so that's the easy part. The harder part is to write function solve. Well, it's not hard. It's harder. So I'm transitioning from this bit set by taking element AI. So I need to cyclically shift this bit set by AI mod S. But my bit set is of wrong size because it must be known in compile time, so I'll have to do it by hand. Does it matter if the values, like set bits, higher than S? Yes, it does. So I cannot allow that. So I'll have to create a bit set like universal that has ones only in positions that are valid reminders modulus. So here I take and with and now I have to restore the answer. For that I will maintain in which cell I'm in right now. I will try to do the transition without taking the element. So sort. Right now I should be in true position, and if I can not take this element and still be in true position, then I'm not taking it, and that's it. Otherwise, I should take it. Yeah. It's something different, but it's probably true. And that should work in n-cube divided by 64. Nice. Very cool contest. Just, yeah, kudos to authors. Thanks for watching. Bye.